So far, we considered counters. We combined flip-flops in various combinations, and we found that we can make counters with them. We can have different types of counters. We can have programmable counters. I can program it to count up, to count down, program it to count in any arbitrary sequence. Counters form one of the key applications of flip-flops. Maybe the next set of applications for flip-flops are registers. See, I think I'm telling too many things. One is the set of terminology that we use, and second is the potential application and the expanse of these. I think you have to pick up all that. So the second set is what is called as a set of registers. We combine flip-flops in a different fashion to form what is called a register. A register is basically a set of flip-flops connected to a particular pattern, just like a counter. In a slightly different form it is connected. And how you look at it, in a counter you look at it as a counter and just connect. In a register, you look at it as something where I can store a number, I can erase the number, I can change the number, I can shift the number, one side, other side. All these things I do with a register. I register a number, I change the number in the register. I erase that number and I take one number in one register, put it in another register. All these operations I can do with registers. So typically the features are I load data into the register. I can load it sequentially. I can load it in parallel. I can read that number. I can load it in parallel. I can read it in parallel. I can read it in sequence. All these, again, just as illustrated with a counter, with registers also, we take 3 flip-flops and just bring out the variety possible. I have taken the same set of 3 flip-flops, flip-flop A, B and C. Just see the connection I have done here. My small change I have made. Blindly, QA I connected to, this is what? QA to JA, QB to, KB to, QB to KB, then, QA to, QA to JA, QA to JB, QA bar to KB, QB to JC, QB bar to KC. I'm getting old, I'm not able to replace things, you have to just prompt me. Okay, my name is Padmanabhan and all that. Just do I hope it is clear. The circuit, the way I have drawn it is clear. Then, at the first flip-flop, I have given an external input. I have given this to JA, I have inverted this and given to KA, just like the D flip-flop. I have given this input to JA, I have inverted and given to KA. This outputs, yes, essentially they form as input to this. This output, B flip-flop output, they form as input to this. Clock signal is same for every one of them. Okay? Now let me see what we do here. I have shown here a clock waveform. I have shown serial data in some arbitrary form. See, I have shown serial data which is 1, 1, 0, 1, 0, etc. One combination I have shown. Whatever the input data coming to the first flip-flop, during successive periods, the values I have shown here. During C0, the value is 1. During C1, this value is 1. During C2, the value is 0, and so on. That is the data on the serial line. Now let me take QA. QA has the J and K values decided by serial data. And any change in flip-flop A will take place at the negative clock edge. See here, this is the negative clock edge. At that time, data is 1. QA will become 1. That's all. Okay, QA will become 1 here, because this data is 1, QA will become 1 here. Going back, if I take this flip-flop, when this input is 1, J is 1, K is 0, at the next clock pulse, this 1 will be transferred here, this 0 will be transferred here. That's all. It's okay? At the next clock pulse. That's what I'm explaining here. Input is 1 at the clock pulse. QA will take state 1. QA bar will be 0. QB, QC, nothing happens because here, as far as these are concerned, when the clock pulse comes, when this clock pulse comes, QA was originally at 1. Okay. I'm sorry, originally at 0. QA was before that, it was at 0. So nothing else happens here because it is at 0 value. Now, at the next clock pulse, this is 1. So this becomes 1. Alright? Now, as far as QB is concerned, QA was at one state, that is input. For QB, this fellow is input. So that decides the next state of QB at the clock pulse. It goes to one state. This 1 gets transferred to QB here. At the next clock pulse, this 1 gets transferred to QC. You see here, sequentially, data is getting shifted. This 1 at the first clock pulse goes to QA, at the next clock pulse it goes to QB, at the next clock pulse it goes to QC. This 1 at the next clock pulse it goes to QA, religiously to QB, to QC. This is 0. Here at this clock pulse, that 0 is loaded to QA. At this clock pulse, that 0 is loaded to QB. At this clock pulse is loaded to C. On and on it goes. So the data, whatever input data you are given here, at successive clock pulses, this 1 is getting shifted, this 1 is getting shifted, this 1 is getting shifted, 0 is getting shifted, 1 is getting shifted. So that data stream, that 1, 0, whatever data stream I have given to the first flip-flop, it is sequentially getting shifted to succeeding flip-flop in the succeeding clock pulses. This is called a shift register. It is a register where data is shifted from the first flip-flop. I got a data here, the first flip-flop. At the next clock pulse, the data gets shifted here. At the next clock pulse, this data goes here. At the second clock pulse, this data, whatever was here, will go in here. Next clock pulse, that will go in here, it will go in here. This is a serial input line. It's a serial output line. It is a serial shift register. Data is shifted in serially and shifted out serially. It's called a shift register. It is a register because it is a set of flip-flops connected to store something. It is serially shifted because the way you are connected, the data moves serially. It is alright? It's okay? Now, the rest of the story is as dull and simple as you have done earlier. See here? Okay, this I have shown here. What will happen? Whatever I explained, I put here. At every clock pulse, data is getting shifted. Now, the transitions occur at the successive negative clock edges. Look, I have added parallel reading facility. Here, I put a read line here. I have taken QA, QB, QC to engage. When I make this high, whatever data is here, that will be available at the output lines. So by this addition to the serial shift register, I have given the facility of parallel reading. Serial input, parallel output. If I take the output from here, it is serial output. If I take the output from here, it is parallel output. I can do serial shifting. I can do parallel output. It's a crudest form of a communication terminal. I take number of flip-flops. I have a data stream coming in one line, 0, 1, 0, 1, 0, 1, 0, 1, and data stream coming in one line. I take 20 flip-flops, all the 20 bits I load into all of them. I do a parallel reading. I can convert any serial bit stream which is coming in and read out as parallel data. It's okay? It is a serial input, parallel output scheme. I added one more confusion here. Here, this, see, I can, if I enable this yes, if I enable this, if I make yes high and L low, if I make L low, this is 0. This fellow is simply disabled. If I make yes high, this data will go through this and become this J and its inversion will be K. Same way, since S is 5, this output will be connected here. So when S is high, serial input will be connected to JA and KA. QA will be connected to JB, QA bar to KB. QB will be connected to JC, QB bar to AC. Is all right? So I have done serial data input by enabling S. It will do serial shifting. If I enable L, if I make L high and S low, please see this. I have done parallel loading. Can you see that? Data is taken from PA, PB, PC line and loaded here. So I can do parallel loading, I can do serial loading. I can take serial output. By combining this, I can take parallel output. Now it is up to you to run riot. You can. Then I will not shift. I will do parallel loading by enabling L. Then make L 0, S high and do serial shifting. So now it is a programmable device. The first step in the program is do parallel loading, remove loading, make L 0, make S high, give data. Where do you want to read? Now what I do, first I will make L high. Okay, L high. Okay, you are talking, don't look at the first one, take the second one. Second one onwards it will be read here. You see this, whatever I put here, by at the time of parallel loading that is available. Then I put the serial input, suppose I make it 0. If I make it 0, at the next clock pulse, whatever was here will get shifted here. Whatever is here will get shifted here. Whatever is originally loaded will get here. So that 3 bits of data that will serially go out. The data you have given here, that will get loaded into first flip-flop. Okay. Serial output will come. If you ask what is going the first flip-flop, that will be decided by serial data input here. I don't know that. Clarify the point. Okay. So I can do parallel loading, I can do serial output. By combining that, I can have serial input, serial output, parallel output. Okay, I just explained the same thing here. Now it is for you to use the register. You can connect in different ways. By connecting in different ways, you can manipulate data the way you want. You just recall what we did with ALU. I am doing a similar thing with flip-flops here. I connect the way I want, and I make it make it work the way I want. I can load data, I can store data, I can shift data, I can transfer from one place to another. I can just do whatever I want with the data. Look here, I have shown 4 registers. I've shown here 4 registers just to bring out the potential of registers. I call as register 1, register 2, register 3, register 4. Here I have got a control signal S1, L1. If I make L1 high, I can do parallel loading of data. If I make S1 high, I can do parallel serial loading of data into this. These 8 bits of this register, I taken this register 8-bit wide, all the 8 bits I connect as inputs here. I can do parallel loading to this. I can do serial loading here. Same way I can do here. Now I can do a parallel loading of data into this. I can do serial loading of data into this by enabling S1 and giving the data. By reading it, I can take that output and give us input here. At that time, if I enable this, I can do parallel loading. After that, I can do serial output. At that time, I can make this active here. I can accept serial data here. I can do parallel reading. You understand what I am saying? I take the first register, I can give serial data. I load. After loading the full 8 bits, I can transfer to this. For that, I do parallel output here by enabling read. I do parallel loading here. 8 bits I load in parallel. So this data which is serially input here, I taken as parallel output, loaded here. This data I can take a serial output and connect a serial input here. Again give clock pulses. With 8 pulses, this data will go in here serially. After loading this fully, I can take parallel output here and load into this register. So I have taken serial data from here, done some manipulation, brought it to this register. What I am saying is, I just shown an illustration. I can do variety of operations. Serial input, serial output, parallel loading, one register, another register, different ways I can connect and manipulate them. To manipulate and get the necessary data, storage, transfer, shifting, all that I have to do is, I have to properly work these signals. This serial signal, load signal, read signal, this read signal, serial, load, all this. These are all the control signals. All these control signals I have to bring out separately, and I ask you, what do you want me to do? You say you do this. I make them high, low, the way I want. And then give the clock pulse, the data will go in. Then you say, okay, from this register I load into that. Again I set the control signals. Do that. I have got a set of registers connected in a programmable manner. I can do variety of data transfer. It's okay? Now, whatever I discussed earlier was a shift register. It shifts from left to right. I can make it shift the other way around. So it's all now, once you understand this, the spirit of that, rest is all very easy. For this J and K, if I use input from A flip-flop, it will be right shift. If I use from C flip-flop and use J and K values here, it will do the left shifting. Okay? So I can do right shifting, I can do left shifting. To do left shifting, I have to enable this side. So this is my R L bar control signal. If I make it high, QA will be the signal going and activating J and K here. It will do right shift. In the other case, QC will be the signal, it will do left shift. Alright? So any register with all these facilities for shifting one way or other way, loading all these together is called a shift register. Now I have gone one step further. I have taken a shift register of 3 stages. A 3-stage shift register I have taken. This output I have connected back here. This output I have connected back here. That's all what I have done. 3 flip-flops. Output of the last stage forms the J input here. This Q bar output here forms the K input here. These are 3 flip-flops connected back to in a circular fashion. And I given a clock signal. This is a shift register connected like this. Is called a ring counter. It's called a ring counter because it looks like in arranged a slightly different fashion, it looks like a ring. Flip-flop A, QA, it goes to JB. QA bar goes to KB. Like this, it just goes like this. It is like a ring. It is called a ring counter. Now let us see how it works. You put a binary number, you load, give a pulse. You put any binary number into the ring counter, you give a clock pulse, every bit will get shifted. Because it's a shift register connected like this, every bit will get shifted. Let's see what happens here. See here, I have got a number 0, 0, 1. This number I loaded here. QC is 1, QB is 0, QA is 0. At the clock pulse, this C is getting shifted to A. This A is getting shifted to B, and B is getting shifted to C. See here, this is a set of pulses, they are getting shifted. This is a shift register. But from the last stage, that output is going as input to the first one. So it will simply go on counting this sequence repeatedly. I think I should show it in a slightly different form, which I have not shown here. The 3 flip-flops, if I put here, load a number, QC, QB, QA. I have loaded a number, now it's not like this. I think I not put it properly here. QC, QB, QA. This is 1, this is 0. At the next clock pulse, this 1 will get shifted here because I connected, that output I connected to this. That 1 will get shifted here, this 0 will get shifted here, this 0 will get shifted here. This 1 will get shifted here, this 0 will get shifted here, that 0 will get shifted here. It goes like this. You can see the shifting. This is a ring counter. This number is also playing around in a ring. It's a 3-stage ring counter. It's very simple. If I got 5 flip-flops, 0, 1, 1, 0, 0. Next state will be, see this 1 will go here. 1, 1, 0, 0, 0. This will be 1, 1, 0, 0, 0. This will be 1, this will be 1. It continues like this. That same number, that sequence will get continuously shifted. It's a shift register. Simple shift register connected like this. It works as a ring counter. That count sequence will be simply repeated. It's okay? Any number you can load. You will just go on circulating. This is a slight variant of the ring counter. It is called a Johnson counter. In the Johnson counter, I take these outputs, so directly putting to J and K, I cross connect this. It behaves in a slightly different fashion. It's called a Johnson counter. You please go through that sequence. It will be slightly different. I showed it here. Actually, functionally it is similar to a binary counter or decade counter. It just counts through something. If I take a binary counter, it counts through sequence 0, 1, 2, 3 like that, or decimal counter. The ring counter, it is a counter because it goes through a sequence, but it's a pattern. The pattern is, the whole sequence moves like this. That's a ring counter. Alright? Now if you ask, where do I use it or how to use it, you are asking me something which I may not be prepared to answer. You are asking what is the application for a ring counter, right? As a student, you have no right to ask what is the application for what I am doing here. You shut up your mouth. Application is a probable question for the examination. Now, that apart, it is, you see, I am telling you there's a flip-flop. R flip-flop, JK flip-flop, master slave flip-flop, D flip-flop, T flip-flop, and all this I am telling you. Then I say you connect this flip-flop, I am getting a counter. You connect in that fashion, you get a counter. You just imagine, sometime in around 1940, somebody said there's a flip-flop. It took 4 or 5 years for people to understand what is this flip-flop business. It will be one state, you give a pulse, it goes to next state. Okay, people were discussing what to do. A lot of papers just on this single flip-flop. What to do with that, how it works. Then over there, from around 40, for about 20 years, people said you can use flip-flop for this, you can use for this, you connect like this, you get this, you connect like that, get like this. So many combinations. Now for people to understand this and say, look, I can make use of that for digital systems, it takes some more time. You understand? So you find those days, variety of people doing lot of things with flip-flops in different ways. Okay, I'll make one flip-flop, you make another flip-flop, all sorts of flip-flops, people taking patents or new ideas, innovative ideas, on and on just going. In that process, some of them have survived. Some of those basic circuits have survived. Survived the vagaries of time. They are these flip-flops, or these combinations. Ring counter, Johnson counter. Now, to come to the point that you are making, the simplest application of a ring counter is Suppose I take 10 flip-flops. I take flip-flop 0, flip-flop 1, flip-flop 2, flip-flop 9. 10 flip-flops. I load here 1, 0, 0, 10 flip-flops. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I connect as a ring counter. I shift it in this direction. When you give one clock pulse, that one will get shifted here. Next clock pulse, that one will get shifted here. Next clock pulse, it will get shifted, this one will get shifted here. Next clock pulse, that one will get shifted here. Okay? I have made a new counter. With 10 flip-flops, I made a counter which will count from 0 to 9. This will be 1, next clock pulse this will be 1, third clock pulse this will be 1, then this will be 1, this will be 1, after that, again that will be 1. So it will count from 0, 1, 2, 3, 4, 5, etc. Up to 9, again back to 0. I used 10 flip-flops to count through 10 stages. Okay. But here, if I take this output directly, I know by looking at it, I know the flip-flop count is 1 or is 2 by just direct look of it. It's alright? I have got a counter with decoder built in. With a binary counter, you have to take that 0101 combination, you have to decode and get output as 0, 1, 2, 3. Here the decoder is not necessary. Is alright? I confused you somewhat. I can use it directly to light a lamp, where I show it as a 1 or a 2. So the counter, by increasing the hardware at this level, I have reduced my overhead slightly. In one case, it is a set of flip-flops and logic gates to get the output. In this case, it's a set of only flip-flops and direct output. Okay, you can use this also as a counter. Wherever you got a batch process, where I want 2, 3, 4 set of activities to be done in a sequence, perhaps a ring counter will be a direct application. In that sequence, for when it is in one state, I would like to put on 2, 3 switches. Next state, another set of switches. A ring counter may be the simplest thing to be used there. I can use a binary counter and do that, but a ring counter may be the simplest one to be used. Yeah, you can do that. Coding you can do that. Directly you can do that. Essentially, it's like a binary counter with built-in decoder. Okay. Now I'm going back. The last century I was talking about accumulator, where I combine number of logic and algebraic functions. I do programmability. Now I have what I call as an accumulator. An accumulator, you see here, is just a flip-flop. I've shown one stage of an accumulator. I take a flip-flop, if I connect it one way, I can make it part of an up counter. J and K, if I define in one way, I can make it count up. If I change it slightly, I can make it count down. If I change it in another way, I can use it as a shift register with left shift facility. Shift register with right shift facility. I can do parallel loading of data. I can read data parallelly as an output. All the facilities built in around a flip-flop, that becomes one element of an accumulator. An accumulator is something which will accumulate data in various forms and make it available to you. I have shown a single bit accumulator here. That shows the function. One control signal CS bar. If you make it 0, it will work like a shift register with right shift facility. When it is 0, you make L equal to 1, shift register with left shift facility. You make P equal to 1, it gives you facility for parallel loading. Now you go back, make that C S bar equal to 1. One can do count up, one can do count down. All these facilities are built in with this here. These are the control signals, L, P, R, C, S bar, and this QA, QB are, they are the inputs and outputs for the previous stages, and stage on either side. So essentially, all the facilities that you discussed with one flip-flop, for registers and counters, all of them are combined and successfully mixed up and seen how you can shift out and do a programmed connection. That becomes a versatile accumulator. So the accumulator is the register flip-flop based counterpart of an ALU. Same functions are shown in tabular form here, not fully. You please fill up wherever the gaps are there. You take it. All the functions you can build in here. A normal accumulator has many more functions. You can increase the size by simply increasing the flip-flops. The basic element is same. As long as you do this parallel operation, you start for everything, the function is synchronous in nature. In any microcontroller, first time I am talking about microcontroller. In any microcontroller, an accumulator and an ALU are integral parts. The typical Intel series microcontrollers, microprocessors, microcontrollers, every one of them has one accumulator. Motorola, their 6800 series, they have two accumulators. Z80, they are to the benefit of both of them, and they have two accumulators and plus some features of Intel. Many microcontrollers today, they have one very versatile accumulator, and there are a number of registers inside which can function as reasonably good accumulators. Big series is like that. One very good accumulator. Others are halfway accumulators. Now you can combine accumulator and ALU. In every microcontroller, every microprocessor, 286, 386, 486, every one of them, Pentium, all of them will have at least one ALU, one accumulator. At least one ALU and one accumulator. So the ALU, accumulator will be, connected to one side. One set of data to the ALU. ALU takes two sets of data. You can add them, subtract them and all that. One set of data will be coming from accumulator, and more often it will be going back to the accumulator. So the accumulator and ALU will work in very close affinity to each other. That is typical of all microprocessors. That's the end of this. You can continue. You want an interval, you can continue. Huh? Yes, sir. Yes, sir, continuing. I can continue. Next is memory. Now we are entering the era of microcontrollers. Memory, I can do? Okay. Memory is basically used to store data and to read data. You store data in the form of bytes. You read data from the memory as bytes. That's the basic purpose of a memory. As you already felt, you can use a flip-flop in different combinations, required combinations, and form memory. Just as you combine flip-flops to form counter and register, with some more effort, you can form memory with flip-flops. We use it for, normally the purpose is you take data, You like to store data for later usage or for archival purposes, or from available data you like to extract some information, or based on the information you would like to take a decision. Now all these are required in microcontrollers. So first you have the memory and then provide the facility for doing all this. There are different types of memories available. As far as we are concerned, we will discuss only memories that go with microcontrollers. Normal microcontroller based systems do not use floppy disk or a CD drive, hard disk drive. These are not used at all. All activities are comparatively smaller in size. So none of them, you take a cell phone, calculator, they don't use very big memory. Of course, today they use memory of the order of 1 megabyte. But even that is very small, it can be accommodated within an IC. Within the IC you can accommodate. So you don't go for that type of big memory. That we will not discuss this. I will discuss here in our scheme. As a prelude to discussing memory, I have to discuss two items. One is called a tri-state buffer. The other is a bus. I will spend some time on this. Then I will get into memory. This adds substantially to the power of memory and data transfer. Basically, a buffer is just an amplifier. You have a signal, that signal used to drive 10 flip-flops. Every flip-flop will take some power. You will find that normal devices cannot supply more than 2, 3 or 4 devices. So you should provide an amplifier, some power boosting device. Such a power boosting device is called a buffer in digital electronics. If the input of the buffer is 0, output will be 0. If the input is 1, the output is 1. That is ordinary buffer. Wherever you put a buffer, you have a choice. You can provide the buffer with a control signal. I have shown here a buffer with a control signal. This is a buffer with X as input. Y is the output. Whatever be the value of X, it will be reproduced here. C is the control signal. C is the control signal here. If C is 1, the buffer is on. There is a link between the two. Input is connected to the output. If C is 0, the connection is snapped. The buffer is off. The buffer is off. It is called tri-stated. So far, we were talking of digital variables where they will take value 0 or 1, high or low, only 2 states. Here, I want to introduce a new state. The output line is simply left floating. I don't commit. Okay, I tell the output line, I have no connection with you, you are left to yourself. It is left floating. It is called a tri-stated output. This is not defined here. Here it is connected directly, here it is not defined. Hence it is called a tri-stated state. Something. 2 more. I have shown alternate form of the buffer. Here, the control signal, if it is 1, the buffer is off. If it is 0, the buffer is on. The control signal is active in the inverted mode. Here it is active in the normal mode. Okay? This is called a tri-state buffer. A tri-state buffer has an input and output. In addition, it has a control signal. The control signal can be active, inactive. If the control signal is active, the buffer is on. If the control signal is inactive, the buffer is off. I am showing how I can make use of the tri-state buffer. See here, this represents the 2-to-1 match that we discussed earlier. One signal, another signal. This is a control signal. If it is high, this is completely off. This is 0, this AND gate is off. This output is steered to this. So if with 2 AND gates and this OR gate, I get a 2-to-1 multiplexer. It is a 2-to-1 match. The same 2-to-1 match I can realize using two tri-state buffers. I take the control signal, I connect like this. If C is 1, this link is off. It's alright? Because that tri-state buffer is off. T is 1, this tri-state buffer is on. C is 1, this tri-state buffer is on. L is connected directly to N. If C is 0, TS1 is off, L is disconnected, but M is connected directly to N. This is another way of realizing a 2-to-1 match, that is using tri-state buffers. When you use a tri-state buffer, I have an advantage also. The other two is simply disconnected. Here that is available as a 0. We'll take more involved cases later on. Buffer is a fundamental element, just like inverter and gate, a basic element. Okay, it's just an amplifier. It's just an amplifier, power amplification. 0 volts you give, output will be 0, but at a much higher power level. Okay. Just to bring out operation of a tri-state buffer, I have shown some scheme here. See here, this one data line. One tri-state buffer, another tri-state buffer. This is a data line. Here there is a tri-state buffer. Here there is a gate. Suppose I keep C2, C3 off. If I keep C2 and C3 off, the two segments are isolated. When I keep this off, it is as though this is one segment, there is another segment. I can operate them completely independent of each other. For example, I can take this A through this data line, I can make it available here. I have to just only put on this. This data is made available here to this AND gate. Same way here, I got this AND gate, I can make this data AND gate output available as an input here. Suppose I keep this off, I turn on this, well, I achieve the thing. If I keep this on, take this, give this on, I have done data transfer from A to this, I can use it here. If I turn on this, I done data transfer from here to here. I can do bidirectional data transfer by connecting tri-state buffers in the proper form. The same data line, this data line is same. In one case I am doing data transfer in that direction, the other case I am doing data transfer in the opposite direction. It's alright? Now you look at the things we have discussed. I have got an accumulator here, I have got an ALU in somewhere, another accumulator, register. I can pick any register, data from any register through tri-state buffer. I put lines all over the place. I connect data to a data line, enabling a tri-state buffer from a register, bring it to an accumulator, do something, take it to another register. It's up to us to do all this. It's okay? So this is what you do. Typical VLS has 10 raised to 8 elements, 10 raised to 6 gates. You put different connection lines, you put tri-state buffers, you connect, do something, do a reconnection, do something else, another reconnection, do something else. You, depending on the reconnection you go on doing, you do different types of operations. Everything is achieved by turning on and off tri-state buffers. One type of elements, one type of operation, another type of elements connection, another type of operation. So tri-state buffer is a key element in any digital system. The way you use the control lines and clear the data, that makes all the difference to it. Now bus. See, if I take a flip-flop output, it gives you one data line. Wherever I have to add, deal data in terms of bytes, okay, a group of 8 bits, it's a byte. I transfer one byte from one register to another register, or add one byte to another byte, or subtract a byte from another byte. Here I am doing all operations in terms of bytes. That means a set of 8 data lines, I am giving a similar treatment. It's okay, the 8 data lines, I will just do for addition or subtraction or data transfer, all of them are treated in a similar fashion. A set of data lines treated in one particular manner is called a bus. It is just like taking data in a bus, taking somewhere, doing something. You put a set of people in a bus, give the same treatment to all of them. Okay? Just as of, not Amrita buses, you take city buses. You take all of them in the bus, Amrita buses are very good. You put everybody in the bus and subject them to the same Tamil song every day in the morning. Okay? Every bit that is inside is done equal justice. Hence it is called a bus. All the bits together given similar treatment. Now when I say it's a bus, the width of the bus decides the number of bits. I can say a byte wide bus or a 16-bit wide bus and so on. A bus can be connected in different ways. I've shown here. I've shown a register here, R1. Another register R2. This shows this line and the number. The two that they show that, look, this bus is 8 bits wide. This register has 8 flip-flops. It can store data of 8 bits. Now, I can take this data, I can give to this register. This is an arrow. Double arrow shows it is an input here. Inside double arrow, it shows an input. So this data bus goes as input data to this register. This bus goes as output data or input data. This bus can turn this side. I can have some other register here. I can take data from here, connect to this, and so on. All these are part of bus conventions. A set, I can